Why do we need control? We need control to run processes safely. We need control to produce high quality products. We need it to optimally use the resources available. We also need control to move processes from one operating point to another operating point. In a typical chemical process, there are a number of unit operations that have to act together in sync. A controller is like the director of a symphony that's operating these processes optimally and safely. Let us consider the blending tank example we had seen a few times in the lectures. It has two incoming streams, one consisting of pure A on the right hand side, one consisting of components A and B, and an exit stream that is at the bottom of the blending tank. Now we can define, based on this process, three different types of variables. Control variables, these are variables of interest that need to be controlled. Manipulated variables, these are variables that can be adjusted, and in this example there's only one variable that we can directly adjust, and it is the pure A entering the tank. There are disturbance variables. These are variables that influence controlled variables but cannot be adjusted. Now, there are two types of controllers that one can design on a process like this. These are feedback and feed-forward controllers. A feedback controller is one that makes use of the controlled variable, measurements of controlled variable, and adjusts the manipulated variable accordingly. A feed-forward controller is one that measures the disturbance variable and adjusts the manipulated variable. In a feedback controller, we measure the controlled variable using a sensor. You pass that information to a controller and adjust the valve accordingly. In a feed-forward controller, we use a sensor to measure the disturbance variable and pass that information to a controller.
Before we get started, I want to give you a quick overview of the different contents of this course. We're going to spend about a month or so on modeling. Modeling is a very important aspect of process control. Before we design controllers, we have to know how processes behave. We have to have a good understanding of their dynamic behavior, and that is done using models. Once we have models, we're also going to have ordinary differential equations. Models have different connotations. In this context, models are ordinary differential equations. And it turns out that ordinary differential equations by themselves are very difficult to manipulate or analyze or solve. And therefore, we're going to be using a mathematical concept called Laplace transforms to study ordinary differential equations. Once we apply Laplace transforms to ordinary differential equations, we will have what are called algebraic equations. We will essentially transform ordinary differential equations into algebraic equations to understand the dynamic behavior of different processes. And then towards the end of this course, we will spend about a month on designing control algorithms. In a sense, we're going to divide this course into 4 different components. In the first component, we're going to focus on modeling, followed by Laplace transforms, that's a bit mathematical, followed by dynamic behavior, an understanding of dynamic behavior of processes. And then towards the end of this course, we'll focus on controller design. Let me try to explain what a controller is using a blending process. A blending process is a very simple process with 2 incoming streams, S1 and S2. S1 has 2 components in it, A and B. It's a mixture of 2 components, A and B. S2 is pure A, and it has a control valve on the stream. S3 is the overflow stream. We're interested in maintaining the concentration of X in S3. W1, W2, and W are various flow rates. X1, X2 are the corresponding concentrations of A in streams S1 and S2. Our objective is to blend S1 and S2 to produce S3 that is at a desired composition. Let's call it XSP. SP stands for the set point. Now there are 2 questions that one can ask. One is called the design question. In the design question, we're going to ask how we can design a blending process if we are given the inlet flow rate and the inlet concentration. How do we determine what the flow rate of S2 has to be so that we get a certain desired concentration in the exit stream S3. We are given nominal values of x1 and w1. Those are represented with a bar on top of those variables, w1 bar and x1 bar. In class, there was a question on what these nominal values are. Nominal values are essentially the typical values of the flow rate w1 and the concentration x1 that you're likely to see when you're running this process. You may not exactly see those values, but these are typical values that you expect when running this process. The question that we want to ask when we're designing this process is that what flow rate W2 of S2 is required in order to maintain a composition of XSP in the exit stream S. In order to solve this problem, we'll have to write component mass balance equations at steady state. We will see later on that to design controllers, we need dynamic mass balance equations. But in order to design a process, we simply need a steady state mass balance equation. There are two ways in which we can write a steady state mass balance equation on this process. There are actually three ways. We can write a mass balance equation for component A, we can write a mass balance equation for component B, and we can write an overall mass balance equation. But it turns out that one of those three mass balance equations is going to be dependent on the other two, and therefore we can only write two independent mass balance equations. Now let's write the mass balance equation for component A. Obviously, because we are assuming that the process is at steady state, mass of A entering the tank must be equal to mass of A leaving the tank. Using that, we can write this equation: W1 bar times X1 bar plus W2 bar times X2 bar is equal to W bar times XSP. Let's call that equation 1. Now let's write the second equation, which is the overall mass balance equation, also at steady state. Mass of liquid into the tank must be equal to mass of liquid out of the tank, which means W1 bar plus W2 bar is equal to W bar. Let's call this equation 2. Now substituting equation 2 in equation 1, we get the following simpler equation. Now since X2, which is the concentration of pure A, is equal to 1, we can simplify this equation further by replacing X2 bar equal to 1. And from the final equation, we can come up with an expression for W2 bar in terms of all the other known quantities. For instance, we know the inlet flow rate of stream 1, W1 bar. We are given the required target concentration XSP, and we also know X1 bar, which is the concentration in the inlet stream S1. Now, given all these values, we can determine the flow rate W2 of pure A that is required in order to maintain the concentration in the exit stream at XSP. So W2 bar, which we have derived here, is the steady state flow rate of S2 required to maintain XSP, or the concentration of X at XSP in S. Now let's ask ourselves a slightly different question. I'm going to call this the control question. The design solution we have derived here is only useful as long as W1 and X1 remain at their nominal values. What if they are changing? In a real situation, an industrial situation, it is never possible to keep the flow rate and the concentration and in the inlet stream at their nominal values. It's very rarely possible. So if those two variables are changing, can we still use the W2 bar that we have calculated using answering the design question to maintain the exit concentration X at XSP? The answer obviously is no. So we have to do something different. So what is it that we can do if W1 and X1 are changing and they don't remain at their nominal values? Now here on the right hand side you see a graph between time versus the concentration X or the set point. The pink line, pink dotted line, is the set point for the concentration. Let's suppose it's 0.6. Now, if there are disturbances in the process, it is simply not possible to maintain your exit concentration at the set point. Your exit concentration is going to hover around the set point. So we have to do something in order to ensure that the exit concentration is as close as possible to the desired value. And I say as close as possible because in real industrial settings, it's often almost impossible to maintain your exit concentration exactly at its target desired value, XSP. So if you are a control engineer or an operator, and if you have to control this process, this is perhaps what you would do. If X is larger than XSP, then you would reduce W2. You will add less of pure A. If X is smaller than XSP, then you would increase W2. You would add more of A. And this approach is what is called manual control. This is a very laborious process, and it has a few disadvantages. It is going to be extremely slow because somebody has to manually do this. It's going to be very inefficient. The person operating the process may not exactly know by how much to change the valve position in order to get the flow rate that one needs to maintain the exit concentration. And on top of it, having an individual perform this task is also going to be very expensive. And for these reasons, manual control is often not preferred. And in fact, with manual control, it is going to be almost next to impossible to control hundreds of thousands of variables in a typical industrial complex. And therefore, we are going to study in this course how to design automatic controllers. Now let's try to see intuitively if we can solve this problem by coming up with a control strategy. Let's propose one. It's not very difficult to propose a control strategy. At the end of the day, a control strategy is nothing but a set of algebraic or differential equations that allow you to determine how one needs to change the valve position in this example. So I'm going to propose the following control strategy where the flow rate of pure A, W2, is going to be equal to W2 bar plus some positive constant Kc times the difference between the set point and the concentration in the exit stream. The difference between the set point and the concentration is what is called the control error. It's the error between the set point and the actual concentration in the exit stream. With this control strategy, we want to use the error as a reference and change the inlet concentration of pure A. So we want to adjust the inlet concentration in such a way that the change in inlet concentration is proportional to the error between the set point and the actual concentration. Now it's very easy to see that this control strategy is actually quite similar to the manual control strategy we have come up with in the previous method. Given that Kc is a positive constant, if X is greater than XSP, then W2 is going to be less than its nominal value. Similarly, if X is less than XSP, then W2 is going to be greater than its nominal value because the control error is positive. Now this type of a control strategy is what is called a feedback control strategy. This is the most widely used control strategy in the industry. Feedback control strategy. So in order to implement a feedback control strategy, we need a few components, a few hardware components. For instance, to run the algorithm we have come up with in this context, we must be able to measure the concentration of X in the exit stream. Let's use a sensor. I'm denoting it here with AT. AT stands for analyzer transmitter. The signal from the sensor must be transferred to a controller. A controller is essentially a microprocessor or some sort of a computer that can process a set of commands. Now in this case, we're going to be coding the above equation for the control strategy into the controller. The controller then sends a signal to the control valve to determine the flow rate of pure A into the blending tank. And this is the feedback controller. Now before I wrap up this lecture, I want to introduce you to some control terminology. This is going to be very, very important in the rest of this course. Without knowing how to separate different types of variables in a process, you will really not be able to design controllers. So pay close attention to this and practice as many problems as you can in order to really get an understanding of what these variables are. The first variable is the control variable. These are variables that you're interested in controlling. The second variable is the manipulated variable, and this is a variable that you have leverage over and you can adjust with a valve mostly, but there are other types of variables where you may not necessarily have a valve for adjusting. You could have something else. A disturbance variable, disturbance variables are those variables that cannot be adjusted. Manipulated variables one can adjust, whereas disturbance variables one cannot adjust. Now in this context, X is a controlled variable, W2 is a manipulated variable, X1 and W1 are disturbance variables.